Yeah, so I'm very happy to continue my lectures on self-normalization, and then I will give a lecture on Taylor's law. Now, we have with us two of the world experts on these fields, so I'm a little nervous, but so Joel Cohen is perhaps the top world expert on Taylor's law, and I defer to him regarding this topic. We have co-authored a paper on Taylor's law, and I am going to talk about it. Then Paul Dukan is a world expert on dynamic processes, and we have a paper on Taylor's law for dynamic processes, and so I defer to him on that. At any rate, I start by self-normalized processes. I would show some applications to machine learning. So let us start. This is a continuation of the talk that I gave on Monday of last week. So this is the front of my book with T.L. Lai at Stanford and Kim and Chow on self-normalized processes. You can see the picture of student Gosset. So self-normalized processes, the first case of self-normalized processes is the case of the student T statistic, where what you have is the sample mean minus nu over the square root of the sample variance over n minus 1. Now, you see we're dividing the sample mean, which is a sequence of IID normal divided by the sample variance. So we have the same variables on the top and on the bottom. That's what we call self-normalization. Okay, so one of the key results in self-normalization is large deviations result by Kim and Chow, in which instead of assuming that you have a moment generating function, you assume that you have IID variables, but no moment generating function at all. So there are no moment assumptions. And the way this is attained is by taking the sum and taking bigger than or equal than root 2 of n times the square of the sum of the squares, the square root of the sum of the squares of the variables. And this to the 1 over n converges to a constant. So this is a breakthrough in large deviations in that one does not assume the existence of a moment generating function. And I think it's one of the key results in self-normalized processes. You can find details on this on the book. Okay, so you can get a comprehensive account of the theory in my book with Lai and Chow on 2009. Now I continue with the technique that I will use, and that is used for many of the results that I cite today, and that is a technique of pseudo maximization, also known as the method of mixture. That for self-normalization we introduced with Michael Klass and T.L. Lai in 2004 in an annals paper. And at any rate, we established a canonical assumption. So we are going to look at a sequence of two variables. So we have a vector of two variables, A and B, with B positive. In this case, we don't make any assumption about the dependence between A and B. So this is a completely general result in terms of dependence. The canonical condition or the condition under which the results hold is the expected value of e to the lambda A minus lambda square B square over 2 is less than or equal than 1, which is in a sense a sub-Gaussianity assumption. Now, this so we are assuming that this result holds for every lambda. And under this assumption, we obtain several results, including a result that has been very important in the development of the theory of machine learning. And I will show that at the end of this section. At any rate, the canonical condition is satisfied by by Brownian motion up to a stopping time. When t is finite almost surely, then the expected value of e to the lambda wt minus lambda squared t over 2 is less than or equal than 1. Okay, so that is a well-known fact in martingale theory. The same thing happens when you have a continuous square integral martingale, and so the expected value of e to the lambda mt minus lambda square, the quadratic variation of at t over 2 is less than or equal than 1. If mt is only assumed to be a continuous local martingale, then the inequality is also valid, applying Fatou's lemma. Now, here I present a result that is rather surprising in my opinion, which is the following result, which appears in my paper in the Annals of Probability on 1999. So this is an old result. So we have a sequence of variables adapted to an increasing sequence of sigma fields. We make, the only assumption that we make about these variables is that they are conditional symmetric. So the conditional distribution of di given the past sigma field f sub I minus 1 is equal to the conditional distribution of minus di given f sub I minus 1. Now, this is the only assumption under which then one can prove that this satisfies the canonical condition. So we have a vector of sums of dependent conditional symmetric variables minus, so we have lambda sum of the I minus lambda square sum of the I square over 2. That expectation is less than or equal than 1. Please stop me if you have any questions. I'll be happy to answer. Okay, so under that condition, so under, for those lemmas, which is Brownian motion up to stopping time, martingale, and its conditional variance, as conditional variation, as well as sums of conditional symmetric variables satisfy the condition, and under only that condition, we get the following result. Probability that the absolute value of A, so this is expected e to the lambda A, minus we have square root of B squared plus expected B squared bigger than X, is less than or equal than the square root of 2 e to the minus x squared over 4. So here, what we have is an almost ideal inequality. So what the canonical assumption is, as I said, a sub-Gaussianity assumption, and the typical exponential inequality holds for IID variables under additional conditions. In this case, we have that sub-exponential inequality up to the expected value of the square root of the sum of the squares, which is easily calculated, is sub-Gaussian. So this result, we are going to prove it, and the tools that are used provided the first, in machine learning, typically people were using heuristics. So they had heuristic arguments to guarantee the optimality properties of their algorithms, but there was nothing with a formal proof. Now, these results show that have been used to show optimal results. So this approach is now very common in the context of self-normalization is very common in the context of machine learning. So now, in order to prove this inequality, we have the following lemma. So I said we were using the method of pseudo-maximization. So the idea is we have a vector of two variables, A and B, and we have probability of, we have that A comma B satisfies the canonical assumption. Then under that assumption, we get that the expected value for any y bigger than 0 of y over the square root of b squared plus y squared e to the a squared over 2b squared plus y squared is less than or equal than 1. Now, I am going to show you how to obtain this result by using the method of pseudo-maximization. And the key idea is to multiply by a density on both sides of the canonical assumption. So let's go to the canonical assumption. So the canonical assumption is that you have an inequality of this type. If I integrate outside by a density that depends on lambda, I can use the fact that this is less than or equal than 1 to integrate on this side. So we can integrate on both sides and the inequality is satisfied. Now the integral over our density is equal to 1. So if I integrate on the left-hand side, this expectation times a density, we get less than or equal than 1. And if we use Fubini's theorem, I can take the expectation outside the integral with respect to lambda of the density. So I have the expectation of the integral of e to the lambda summation of d sub I. Okay, expectation of the integral with respect to lambda of e to the lambda sum of the I minus lambda square sum of the I square over 2 density of lambda f of lambda d lambda. Now, one interesting thing that happens when you integrate is that in that situation, when you integrate over lambda, the sum of the I squares and the sum of the I square over 2 become constants. So this allows us to play with them as though if they were constants and then take the expectation. So I will show you an example of this, and that will give us this inequality. So if we multiply both sides of the canonical condition by a density which depends on lambda, it's a normal density, so it's 1 over the square root of 2 pi times y is any number bigger than 0, e to the minus lambda square y square over 2. This, so we are multiplying the canonical assumption, as I said, by a density of lambda, d lambda, and then we take so the integral outside will be less than or equal than 1. Then we are going to use Fubini's theorem to take this expectation inside. I mean, this integral inside. And we have the expectation outside. Now, when we integrate this with respect to lambda by completing the squares on this term, we can get the following. We have expected y over the square root of b squared y squared e to the a squared over 2b squared plus y squared times. This term doesn't depend on lambda. So this will be times the, times the integral from minus infinity to plus infinity of the square root of b squared plus y squared over the square root of 2 pi. And then we have e to the minus b squared plus y squared over 2 times this quadratic form which is basically a Gaussian. You see, we can factor out a over b squared plus y squared. So we have a Gaussian with mean a over b squared plus y, an appropriate variance related to this constant, d lambda. So this integral, since we have this is a density of a Gaussian variable integrated over d lambda, this integral is actually equal to 1. Is there any question about this? So we have that this integral is 1, therefore the expected value of y over the square root of b squared plus y squared e to the a squared over 2b squared y squared is less than or equal than 1. So that proves the claim that I had made originally. You see, we have obtained an exponential bound on a squared over b, a function of a squared over b squared. This bound allows us to, by using Cauchy-Schwarz, allows us to get the appropriate bound that will give us the exponential inequality that I stated initially. So let me show you this. Now, this expected value is actually one of the key tools that are used in machine learning to obtain algorithms for machine learning, and as I will describe later. So again, I have introduced the way of proving this inequality, and now we are going to use Cauchy-Schwarz, and we showed that the expected value of e to the a squared over 2b squared plus y squared is less than or equal. So this function is equal to the of e to the is equal to is less than or equal than expected value of y e to the a squared over 2b squared over b squared plus y squared to the 1/2 times the expected value of the square root of b squared plus y squared over 2. You see, I can separate things, and when I take the square of this quantity, I get e to the a squared over 2b squared plus y squared. And that's what I have here. I multiply by the square root of b squared plus y squared on both sides, and then use Chebyshev's inequality or Cauchy-Schwarz. And I have shown that this expectation is less than or equal than 1. So I obtained that this bound, I obtain a bound on the expected value of e to the I squared over 4b squared plus y squared in terms, this is bounded by the expected value of the square root of b squared over y squared plus 1 to the 1/2. And then we notice that the square root is a concave function. So I can bound this expectation by the expected value of b over y plus 1. Now, since y is any number bigger than 0, I can replace it by expected value of b, and this gives me that this expectation is less than or equal than 1, than 2. So this is b over expected value of b over expected value of b plus 1. So that's less than or equal than 2. And this gives me the bound expected e to the a squared over 4 times b squared plus expected b squared less than or equal than the square root of 2. Now, we use Markov's inequality to get the bound probability that the absolute value of a over the square root of b squared plus eb squared bigger than x. Then I square this term and multiply and divide by 4. So I have this equality. And then I use Markov's inequality to get the bound square root of 2 e to the minus x squared over 2. Now, let me see what I have next. Okay, so let me just discuss the importance of this bound. As I said, the canonical assumption is satisfied by conditionally symmetric variables. So if you have IID variables with just a conditional, which are conditional symmetric, our assumption can be just the expected value finite, but not the square, not the second moment, just the expected value of the variables finite. They don't have to be independent. They can have any dependent structure, but they have to be conditional symmetric. Is less than or equal than the square root of the sum of the squares plus this expectation, less than or equal than e to the minus x squared over 4. So this takes us to a situation where we get exponential bounds, even in the case where the variables have infinite variance. And so this is satisfied by heavy tail distributions. So this is you don't have to have a variance to use this bound. And Bercoux et al. In a book which Paul has put on the website, have used this bound to obtain several, so they show several applications of this, including to the case of branching processes, autoregressive processes. So all of these satisfy the canonical assumption. And for those, you can obtain this inequality. I refer you to the book by Bercoux et al. For the applications. Now, again, I am going to go back to the canonical assumption. So assume that you have the canonical assumption. One of the key theories one of the key results in the theory of sums of independent variables is the law of the iterated logarithm of Kolmogorov. In this result, what he chose is the following. He chose that the lim sub of the sum of di squared, so I assume, okay, so Kolmogorov obtained this result when you replace this by the variance, so sum of the variance, so it's n square root of n log n times the variance. Now, what I just proved allows us to prove, to obtain a law of iterated logarithm without assuming that there's a variance. So you can, for example, Kolmogorov's LIL assumes that you have a variance and the lim sub is less than or equal than 1. You see I have square root of 2 here. But the result that I showed, okay, so the canonical assumption allows us to get this LIL, this law of the iterated logarithm, for conditionally symmetric variables, for example. So we don't assume anything about moments of the variables, and we get an LIL, except for conditional symmetry, on the case that the sum of di squared is infinity, the limit is infinity. Now, one might think, or one question that bothered me for several years was, can I extend this to the case of arbitrary variables as opposed to conditional symmetric variables? And one can do this by using a symmetrized version. And this result, which I would show later on, which is a new result, can be obtained by using the theory of decoupling. So I'm going to give you a 2-page introduction, self-contained 2-page introduction to the theory of decoupling, which then allows us to understand this new LIL without any moment or dependence assumptions or conditional symmetry for arbitrary variables, which would then allow you to, for example, plug in sums of Cauchy variables, IID Cauchy, and then so the lim sup of the sum of IID Cauchy variables over the square root of 2 sum I going from 1 up to 1 x sub I squared log of the sum of di square is less than or equal than 1. So this is a result that has a lot of applications. Well, I spoke about machine learning results. Now, the extension of this result, as I will describe later, should be has potential for applications in machine learning where you don't make any assumptions. So let me just show you the result. So I'll show you what the result is, and then I'll do to motivate you to be patient on understanding decoupling. But the universal LIL is as follows. So I have di f sub I, so I have a sequence di adapted to a filtration f sub I of arbitrarily dependent variables without moment assumptions. And what I do is, using decoupling, I can find a sequence E sub I, which has the same distribution as di, and is conditionally independent. And when I take the sum of di minus ei, which I can obtain by using the random mechanism that gives me di, then the lim sup of the sum of di minus ei, the symmetrized version, over the square root of the sum I going from 1 up to n di minus ei square log of the sum I going from 1 up to n di minus ei square is less than or equal than 1. On the set where the sum of di minus ei square is equal to infinity. Now, this is a symmetrized, self-normalized extension of Kolmogorov's LIL to arbitrarily dependent variables without moment assumptions. So having stated the main result, which is a new result, I haven't published this result, and it follows from the theory of decoupling. So I'll show you the result, the theory. I'll show you an introduction to decoupling. Now, so there is a book which is the book that discusses decoupling, which is a book with a very Cine in 1999. And I have a survey, up-to-date survey of these results of decoupling up to 2019 in the notices of the American Mathematical Society. Now, this journal, these notices go to all the members of the American Mathematical Society, which is over 30,000. So this paper has had some impact in all of mathematics. At any rate, so let me discuss what decoupling, the origin of decoupling is. So we all know the theory of martingales, which is central to the development of modern probability theory. The theory has been extended widely through the introduction of conditional independent tangent decoupling. And just to give you an idea of how widely applicable this result is, the Kolmogorov-Smirnov result, Kolmogorov-Smirnov statistic, which is used to test for the distribution function of a variable, can be extended to sums of variables, sums of f of xi, xa. So you can extend Komorov-Smirnov to the case of U statistics or U processes and apply this, apply decoupling. Now, decoupling, the first result on decoupling is appears in a paper by Burkholder, where Burkholder and one of his students, McConnell, were trying to extend the theory of martingales to Banach spaces, and they attained this by using decoupling. So martingales, of course, you need to assume that they are real or they are in Hilbert space, but there was an attempt to extend this to Banach spaces and empirical processes, and this was attained by using decoupling. So let me show you an introduction to decoupling. So this is a brief introduction to decoupling, and if you want to see the state of the art, you look at my paper in the notices of the American Mathematical Society, is the November issue in 2019. So here we are going to first introduce a definition. So two sequences DI, EI of variables, of random variables adapted to the sigma fields F sub I. So I'm assuming that there exist two sequences of random variables. Then DI and EI, the sequences are said to be tangent with respect to F sub I. If for all I, the conditional distribution of DI given the past is equal to the conditional distribution of EI given the past. Okay, so tangency basically means that the conditional distributions are the same for the two sequences, which are adapted to F sub I. So we have two sequences adapted to one filtration, F sub I, and which could be the sigma field generated by the DIs and the EIs. So I assume that I have these, then I say, now, under this assumption, we call these two variables tangent, okay? So we take, so the variables, a sequence of variables that satisfies this condition is called, the EI is called a tangent sequence to DI. So now, a very important result in the theory of decoupling is the following. For an arbitrary sequence of variables adapted to an increasing filtration F sub I, one can always find a sequence E sub I of random variables. The E sub I's are now conditionally independent. You can construct them. In that way, I will show you the construction. And so they will be, the E sub I's are conditionally independent with respect to the sigma field generated by the D's. So what we have is, in decoupling, what we're doing is we're looking at functions, expected values of functions of D1 up to Dn, and relate them to the expected value of functions of E1 up to En, where the E1 up to En are conditionally independent. So this allows us to transfer results for the independent variables to the case of dependent variables. So one can extend, for example, the moment generating function of the sum of DI is bounded by the moment generating function of the sum of EI times constants. And this allows you to extend, for example, the martingale Bernstein's inequality for martingales to the case to the case of self-normalized martingales. So the result for independent variables to the case of self-normalized martingales. Okay, so how do we construct this sequence? Now, if there's any question about this, I'll be happy to present it again, but at any rate, the structure of the construction is very simple, and it first appeared in a paper of mine in 1994. Before that, decoupling was basically set up in an abstract setting, and so it was hard to decide which one would be a decoupled sequence. By using this construction, you get a particular decoupled sequence that has the condition that it is conditional independent and can be used in applications. So to construct the EIs, what one does is you assume that you have access to the random mechanism that produces the DIs. So what we do is we take two independent copies of DI, and I call one of them E1 and the other one D1. So I have two independent copies of D1. Now, I am not assuming anything about the distribution of the variables, and I am constructing two independent copies of that, okay? In my book, you can find a graphical description of this. Okay, so having obtained the first E sub I, which where I have E sub I are conditionally independent, what I do is the ith variable is constructed. So having constructed D1 up to Di minus 1 and the respective EIs, then the ith pair is obtained by repeating the using, okay. So we are going to use, we condition on the sigma field generated by the DIs up to I minus 1 and EI, okay. Okay, so we know what this distribution is, the conditional distribution of this. EI is basically an conditional independent replica of DI. So basically we have a sequence of variables, D1 up to DI, and we know how to produce, or we have a mechanism for reproducing the dependent structure. So we take two independent copies of DI given F sub I minus 1, and we obtain E sub I. So, okay. Now it is easy to see that if I take F sub I prime to be the union of the sigma field with respect to the D's and the sigma field with respect to the E's, what we have is a sequence, the sequences DI and EI satisfy that they have the same conditional distributions. Moreover, the conditional distribution of, which this conditional distribution is the same as the conditional distribution of EI given the sigma field generated by the D's. Okay, so the sequence E1 up to En satisfied, because of the construction, satisfies the condition that it is conditional independent given the sigma field of the D's. So a sequence EI of random variables satisfying the above conditions is said to be a decoupled tangent version of DI. Okay, and moreover, if I take the difference between DI and EI, what I obtain is a sequence of conditionally symmetric variables given F sub I prime. So I am able, for any sequence of variables, adapted sequence of variables, I am able to construct a sequence of variables such that when I take DI minus EI, this new sequence is conditionally symmetric. Now, I want to remark or stress that the DIs don't have to be identically distributed or independent. The DIs can have any dependent structure. So this allows us to symmetrize arbitrarily dependent variables, okay? And the result will be conditionally symmetric. So then using this, we obtain the universal law of the iterative logarithm. So what we have is, since the sequence d sub I and e sub I are adapted to the same sigma field, in this case, if ds sub I prime, which is f sub I, or the sigma field with respect to the d's, maximum with the sigma field with respect to the e's, then I have that the lim sub as n tends to infinity of the sum of di minus ei over the square root of 2 sum of di minus ei square log of the sum of di minus ei square less than or equal than 1 on the set where the sum of di minus ei square is equal to infinity. Now, what is, so as I said, this is a new result. This is a symmetrized version of Kolmogorov's LIL for arbitrary variables. And as you will see, the LIL, the law of the iterative logarithm, is instrumental in the development of sharp algorithms in machine learning. So, so that's what I would show next. Okay, so the first example where decoupling was used in machine learning that I know, I receive whenever there's a paper on machine learning citing my work, I receive an email from Google. So, and there I found this result. So now it's an improved algorithm for linear stochastic bandits. Now, stochastic bandits basically are related to the way in which, for example, Netflix picks the movies to show you. So basically, the way they do this is they present you with a sequence of, what they do is they have a training sample, which is basically a group of people, and they present them with n movies. And then from that, they predict which movie they will select next. And that is based on the voting on which, what type of movie is more interesting for each one of the individuals. So this is a technique that is used by Netflix. Now, so this paper, which introduced the theory of decoupling into machine learning, cites my work, in particularly the inequality that I just presented. So you see, in their proof of their main result, okay, they assume the canonical assumption. They use the canonical assumption, okay? They show that expected e to the m tau lambda less than or equal than 1. And under this canonical assumption, they, by using the theory of self normalization, they show this bound, which is basically a bound that they use to construct their algorithm. So this bound, which is their key result in showing their algorithm, is basically obtained from theorem 14.7 in the book. And I want to show you the result that is used. So theorem 4.7 of the book on decoupling with Lai and Chow basically is an extension of the result that I showed you how to prove to the case of, for the matrix case. So you see we have the square root of the determinant of V. So V is any positive definite non-random matrix over the determinant of C plus V. So they satisfy the, A and C satisfy the canonical assumption, times e to the 1 half A prime C V plus V to the minus 1 half A, and that is less than or equal than 1. And then we have the same, by using Cauchy-Schwarz, we obtain the same result as the one I stated. So let me go back and show you that this is basically an extension of the result that I proved. And so just remember the form of the result, and I'll go back and show you that indeed this is a sort of simple extension of what I proved. And so I'm going back to show you the result that we proved. So this gives you a flavor as to how one can prove self-normalized results that are important in machine learning. And so basically the bound that we have is that expected value of, under the canonical assumption, is expected value e to the a square over 4b squared plus expected b squared. Well, in this case, this can be replaced by y for any y bigger than 0, less than or equal than the square root of 2. And this is obtained, so this gives us a bound on the expected value of a squared over 4b squared plus y. And this bound is basically obtained by looking at this expectation. And in the matrix case, A is the matrix. And so what we have is we had A and C. And C is basically a constant matrix, which what you do is you take the determinant of the matrix, C. So we have the same result except extended to the case of matrices. So now the extension to the case of matrices was used to obtain the algorithm that that provides the main result in the paper, Improved Algorithms for Linear Stochastic Bandits. Now, as I said, this is the first paper that uses self-normalization to provide algorithms. So this was obtained in 2011, and it was published in the main conference on machine learning, which is basically the main venue to publish results in machine learning. The tradition in machine learning is to publish results in conferences, and that's sort of like the main venue for publication of their breakthroughs. Okay, so now I'll connect the LIL, the law of literal logarithm, to machine learning. So it connects basically the LILs that I have presented to the case of machine learning. And the algorithms that they use are basically on the bounds on the LIL. Okay, so there is so the title of this paper from 2014 is an optimal exploration algorithm for multi-arm bandit problems. So this algorithm shows us that if you want to get optimal algorithms, basically what you do is you take the sum of your x sub i's, and the first time that this sum is bigger than the boundary, square root of sigma square times t, or n log of t, or n, this algorithm, the algorithm that is basically based on the LIL, so this is, remember that the LIL is the square root of the sum of the squares. Okay, this is basically using Kolmogorov result, which is not self-normalized. And it is basically for IID variables. Now, so if you want to obtain sharp results for IID variables, what you use is the bound on the LIL. So if we think about the movies in Netflix, the best algorithm for picking which movie to show next to an individual is going to depend on the LIL, the law of the third logarithm. So you remember we have multi-arm bandit problems. So each arm corresponds to one of the movies that are being discussed. So the training sample, basically what it has is an initialization of their algorithm, and then they are going to find the optimal algorithm, or the optimal algorithm for which movie to show to an individual by basically voting. So they train their algorithm, and then they show new movies so they take any, so they are going to look at which movies, so they can select movies, and then in the end decide or show which movie the individuals pick, and then they adjust the next movie to obtain. And when the number of movies reaches that are selected are right, when the predictions are right, and the number of movies satisfies or the appropriate movies, the appropriate selection satisfies an LIL bound, then they declare that as the actual bound for their algorithm. Okay, so that ends my presentation on machine learning and self-normalization. So I'm going to take a pause to take questions on these topics. So are there any questions regarding these topics? Okay, so there are no questions. I'm going to take a moment to rest a little bit, and I'll come back to the Taylor's law the presentation on Taylor's law. Okay, so
so this means that you make a little break, okay?
Excuse me? What did you say?
Are you doing a break?
The next thing is going to be Taylor's law.
Okay. So, but do you want to have some break, or do you want to?
Yes, perhaps a 5-minute break would be in line so that people can, you know, perhaps the self normalization was tiring. So let's take a 5-minute break, and I'll come back in 5 minutes to answer questions on self normalization. And so now, in a minute, I will start the presentation on Taylor's law. So in this, I was very fortunate to be present at a talk by Joe Cohen, where he presented Taylor's law. And so in his presentation, and basically the theory of Taylor's law was based on an assumption on the actual expectation and variance of random variables. So it was Taylor's law was using the actual moments of the variables. And what I was able to do is to introduce self-normalization into the theory. And I'll tell you why this is important. At any rate, so the next presentation is going to be a new method to do self-normalization. So okay, so here is the new method, and let me just talk a little bit about Taylor's law. So Lionel Roy Taylor, who lived from 1914 to 2007, was a British ecologist, and he published a paper entitled Aggregation Variance of the Mean in March 4 of 1961 in Nature. The journal is called Nature. In that paper, Taylor studied the relationship between the mean and the variance of population densities for at least 22 biological species of bugs. They're called aphids in 24 data sets. Now, so he had 22 species, and for each one of these species, he had 24 points. On the log scale, Taylor's law showed that the mean variance relationship between these data points was well described by a linear equation on the log of the sample variance. So the log of the sample variance equal to the log of a constant plus what we call B, which is another constant, times the log of the mean. Now, so I'll show you a little bit about this. So now, this is the formal introduction. So Taylor's law has been used as a tool in studies in demography, biology, that was Taylor's original result, physics and mathematics, among others. So thousands of papers have been dedicated to the study of Taylor's law. Important surveys on this topic are by Kendall, Eisler, and Meng. And this talk is partly based on work with Mark Brown and Joel Cohen, and on work with Paul and Yahya. Okay, so here is the way in which Taylor's law is stated. So in a multiple set of samples, the variance of the population density is proportional to a power of the mean of the population density, which means the variance is equal to A, a constant, times the mean to a B. And when you transform to the sample mean, when you transform this into the log scale, you get the log of the variance is equal to the log of A plus B log of the mean. And this is equivalent to say that the variance over the mean to the B is equal to A. Okay, so his model, basically that has been shown to be satisfied by multiple biological, financial, and numerical series. Actually, prior to what I will show you, even though the empirical usage of Taylor's law is in both samples, rather than the actual connection to Taylor's law is by using the actual variance of your variables divided by the mean to the B, the actual mean. So the theory of Taylor's law, the actual theory, has been developed assuming that you know the variance and the mean to the B. So what we were able to do is to extend the theory to the case of sample variance over the sample mean to the B. And the idea is that we now have an extension of the mathematics of Taylor's law to the case of samples, which was the original study of Taylor. Now, here it shows, this is the picture of Taylor, and each dot here, okay, represents, is the mean and variance. So you see log mean and log variance in 1 year from sites in Great Britain of one species per line. Okay, so you have different species, and there's a connection between the sample mean of the particular species and the sample variance. So they took means and variances at different locations, 24. So they basically took a sample of size 24 at different locations, and they calculated the sample mean and the sample variance, and for each species. So what they found was that for the same species at different locations, the relationship between the sample mean and the sample variance was basically linear in the logarithm scale. And this was the beginning of Taylor's law. So Taylor basically did the study and observed that there was a linear relationship. He actually didn't work in the log scale, but this is, once you transform things into logs, this is the example. So basically what this allows you to do is to use regression. Suppose that your new sample has a mean, a given mean, but you do not know the variance, then using this, you can calculate the variance or estimate the variance for the population, how variable the population is. So, for example, in the case, one of the studies of Taylor's law has involved the location of tigers in Siberia. And so they're looking at the number of tigers in various parts of Siberia. And so they take a sample That is to say, they take an independent samples on each location, and then they plot the sample mean and the sample variance at different locations, okay? And they find that no matter what the location they sampled, the mean and the variance of the number of tigers follows a straight line relationship. So this is a very useful result in the study of the behavior of tigers. Okay. Another place where, which is important in an example of Taylor's law, is a paper by Joel Cohen, Chu, and Bromberg in 2013, in which they studied the population, the mean and the variance of populations of 18 counties in Norway in 1978 and 2010, through 2010. So basically what they notice is that the log of the mean of the population density was related to the log of the variance by a straight line. So if you know the mean of the population density, that gives you a good estimate for the variance. Now, okay, so that ends the introduction. Now I'm going to go to a different file. And so what I do is I connect the Taylor's law to the coefficient of variation, squared coefficient of variation. So we have the squared coefficient of variation is defined as the sample variance over the square of the sample mean. The coefficient of variation provides a measure of dispersion which is invariant under scale. Okay, so it's a measure of dispersion which is invariant under scale. As such, it is a useful complement to the variance, which is a measure of dispersion. So given a set of temperature measurements on the Celsius scale, the coefficient of variation is the same as the one in Fahrenheit scale. However, this is not the same as the variance. In the variance, depending on which scale you're working, that will change the coefficient of variation. Okay, so it's difficult to interpret the results on the spread of your population when you change the scales. Now, Taylor's law satisfies, in a particular sense, the scale invariance. So, Taylor's power law is a generalization of the coefficient of variation. It is an important criteria used to describe the dynamic of populations. It was first observed as an empirical pattern in ecology, where it was noticed that the variance of each sample was approximately proportional to a power of its sample mean. So an important property of Taylor's law is that it is invariant under scale change. Taylor's law has been widely used as an explanation of numerous phenomena, including population growth, in which samples at multiple locations at a point in time are replicated at several points in time. So again, as I discussed before, so basically this is a copy of what I discussed before, so I'm going to skip. This talk is partly based on joint work with Mark Brown and Joel Cohen. Now, I want to remark that the way in which the samples were taken was assuming that you take IID samples. In work with Paul Ducan and Yahya, we were able to extend that to the case of processes, dynamic processes, including arch and arch processes. Okay, so I'm going to set up the sample version of Taylor's law. So this is a theoretical approach to Taylor's law that allows you to calculate the variant, the bias on the sample population, the sample mean, the sample variance over the sample mean to a power, to the variance of the distribution that generates the samples. So we have a sequence of a double array of non-negative variables, okay, where for each j, we have IID variables. So what we have is the sample mean for a fixed j is given by this, and the sample variance is the sum of xij square minus x bar square over n minus 1, nj minus 1. Now, Taylor's law is said to hold if we have the log of Snj is approximately a constant times, in the example that I presented before, it was b instead of alpha, constant times b times the log of xnj. So for fixed finite constant c. So the way in which Taylor's law is used is basically for each species, as I described before, there's a different parameter b or alpha in this slide. And so once you identify using regression what parameter is in the log regression, you can then use that for a given species. You can do the prediction of the spread of the species given on the number of on the average of the population. Is there any question? Okay. So our main results are explicit formulas for the expected value of Snj square over x bar nj to the alpha or to the b as discussed before, and the variance of xnj over xnj to the b for j going from 1 up to bm. And this expectation is obtained in the context using Laplace transform of the distributions of the original variables. Okay. So if you know that the distribution of your variables is exponential, say, for a given species, then by using this, you can find the bias of your sample. You see the difference between this expectation and the actual variance divided by the mean to the alpha or b. And okay, so in this case, what we show, or an example shows that the variance of the log of this ratio is greater than or equal than the variance of the square of the sample variance over the sample mean for nj less than or equal than 10. Basically, And this justifies our approach to the study of Taylor's law. So what we do is we study Taylor's law in the context of the sample size being small. So as I discussed before, so Taylor used sample sizes of n equal to 24. And he had 24 samples, a sample of size 24 for each one of 18 species. Now, sometimes to obtain the samples, the sample size, it is very costly to obtain a sample of large size. And what we do is we show that our work, our approach, basically based on the sample variance over the sample mean to the alpha, is has a better variance value. It has a smaller variance, so it's better to work on this arithmetic scale than on the logarithm scale when you have small variance, small sample sizes. Okay, so we treat Taylor's law as an inverse problem. That is, we say that Taylor's law holds with parameter alpha for all distributions fj, for which the expected value of Snj squared over x bar n to the alpha is equal to a function of the distribution times alpha n of alpha nj. Again, in this case, alpha is the what I call b in the original slides. So I'm sorry for this, change of notation. So at the end of this talk, I will present an example with respect to exponential distributions, which is a special case of the gamma distribution. For alpha equal to 2, or in the case that we studied earlier or presented earlier, was p is equal to 2. So a reduction. Without loss of generality, we can drop the subscript j. And so we look at a sequence of positive IID random variables and a given distribution function f. So we are calculating the expected value of the sample variance over the sample mean to a constant in terms of a function of the distribution alpha and n. So what we are able to do is, suppose that you know the Laplace function of the distribution of f. Then we can say that Taylor's law holds with parameter alpha for all distributions for which k of f alpha n is equal to a positive constant. So this is really an inverse problem. So suppose, and this is the reason why Taylor's law is so important. So rather than discussing the dependence structure of the variables, what you do, well, you're sampling IID. And what you're going to do is, once you calculate the parameters, okay, once you find a linear relationship between the sample mean and the sample variance, the log of the sample mean and the sample variance, or basically an equality between, approximate equality between the sample mean over the sample variance to a power. So the given power, which is basically the slope in the log scale, that power is linked to a certain distribution. So the idea is, if you know what the power of your samples is in the log scale, this will then take you to what is the this tells you what the distribution of your variables is. Okay, so let's go to, so is there any question about how this inverse problem is? So basically the idea is you have your sample variance and your sample mean to a power. So you plot your sample variance and your sample mean. By looking at the log scale, if you have a straight line using regression between the sample mean and the sample variance, the log of the sample mean and the log of the sample variance, and you can calculate a B, a particular alpha or B, depending on which notation we have, that will give you, once you know B, that gives you the distribution of the variables. So it's an inverse problem. So for example, the distribution of the number of the distribution of the number of bugs in the sample, or the distribution of the number of tigers in given samples. Okay, so now let's go back to the coefficient of variation. Suppose that you have a mean different than 0 and a variance which is finite. Let's assume that actually the variables, the mean is bigger than 0. It is common for to use sigma square over nu square, which we call the square coefficient of variation, as a measure of variation between random variable x1 over nu. Okay, so it is common for sigma square over nu square to be called the square coefficient of variation, since its variance, it is the variance of the random variable x1 over nu. And it is unitless, you see. So you have the variance of this quantity sigma square over nu square. And this quantity basically doesn't have any units, because x1, if it was in pounds, nu would be in pounds as well. So it's a natural spread measure of spread, which is unitless. Now, an empirical estimator of sigma square over nu square, the natural empirical estimator is the sample variance over the sample mean square. Now, it is easy to see that when the x's are non-negative, the expectation is given by k of f comma 2n. Okay, so k was basically the function of the Laplace transform that I will present. So the coefficient of variation is going to be presented as a function of the Laplace transform of your distribution. So this connects our results to the square coefficient of variation. However, our results require that the x's be non-negative. So one can work on extending our approach to the case of non-negative variables and extensions to the non-IID variables. Now, a remarkable fact is that because of cancellation, the population variance could be infinite, but the sample mean and the sample variance are always finite. So what this tells us is that we can, for a sample of variables with heavy tails, we can calculate the coefficient of variation, the sample coefficient of variation, whereas the population coefficient of variation could be infinite. And this is important in the context of mathematics of finance, because a lot of cases in mathematics of finance, the sample variance of the distribution is infinite. But when the population of the distribution is infinite. But what this shows us is that you can still connect, even though the variance is infinite, the coefficient of variation is going to the sample coefficient of variation will have a mean which is finite, even though the variance of your variable is infinite. Okay. Any questions about this? How this works? Now, the main result, I will now present the main result. So we have a sequence of IID non-negative variables with alpha bigger than 0, is a constant. In what follows, we provide a closed form expression for the expected value of Sn squared over x bar n to the alpha. Okay. When n is finite, in terms of a function of the Laplace transform, phi of lambda, that is to say, expected value of e to the minus lambda x. So basically, this gives you the expected value of the coefficient of variation when you divide by xn squared. So what we have is for any distribution, non-negative distribution, we can calculate the expectation of this function, sample variance over sample mean to the alpha. It doesn't matter if the distribution has a heavy tail. This, we can calculate the expected value, or an infinite mean. We can calculate the expected value to the alpha as long as this expectation is finite, which in the case of heavy tails, the expectation will be finite. So the formula that we have is that the expected value of the sample variance over the sample mean to the alpha is equal to this expression. So it's n to the alpha over gamma of alpha, integral from 0 to infinity, lambda to the alpha minus 1, the Laplace transform to the n minus 1 times the second derivative of the Laplace transform times the Laplace transform minus the first derivative squared d lambda. So basically, for the case of the coefficient of variation, so the sample coefficient of variation will have an expectation which is of this form. You have xn squared here, so you have n squared over gamma of 2, which is 1, times the integral of lambda to the 1, then the Laplace transform of your distribution, d lambda. So this is important in the study of the spread of distributions, in that you can calculate the expected value of the sample coefficient of variation in terms of the Laplace transform of your variables. I would show how this is, or perhaps let me say something about this. In the case your variables are exponential, for example, this expectation will be constant for the sample variance when the variables are exponential. So this is an inverse problem. Suppose that you know the coefficient of variation, so here alpha is equal to 2, and that coefficient of variation, when you plot it, looks at when you take different samples, the relationship between the sample variance and the sample mean in the log scales is a straight line. This tells you that the variables have a distribution which is exponential, as I will show later. So what we have is an inverse problem. This allows you to take the samples and from then infer what the distribution of your variables is based on the coefficient of variation. So you can test the hypothesis that your variables are, for example, exponential based on your sample, the sample coefficient of variation. If you have a straight line, then you know that the distribution of your variables is exponential. So it's a different way of doing the test of hypotheses for arbitrary distributions, once you know their Laplace transform. Okay. Now, let me skip this. So let me say, when you have a gamma distribution, if I take beta to be a constant, then, or let me go back a little bit because this might be confusing. Let me see. I apologize for this. Okay, so anyways, the method that we use to obtain the result is a method introduced by Karamata in the 1930s. There's a famous result of Karamata called Karamata's theorem, which is very important in large deviations. This approach is based on a different result of Karamata, which is basically related to the following. I'm sorry about this. I'm going too fast, so let me see. Okay, so okay, so the density of the gamma distribution with parameters alpha and beta is basically beta to the alpha. Again, I apologize for that. When I use the mouse, things go very fast. So I'm just going to skip using this. Okay, so the density of the gamma distribution is beta to the alpha over gamma of alpha, lambda to the alpha minus 1, e to the minus lambda beta. When you integrate that, you have 1. So basically, we're using a variation on the method of mixtures. If you let beta to be random, okay, by Fubini's theorem, you're going to have that the expectation of beta to the alpha, alpha is constant over gamma of alpha lambda to the alpha minus 1 e to the minus lambda beta, the lambda is going to be 1 if beta is a random variable. So this is the fact that we use. So you see beta, we take the beta to the alpha to the left-hand side. In Taylor's law, we are looking at a ratio of a sample variance over the sample mean. Now, looking at ratios, the expected value of ratios is a quantity that has eluded theoretical development for several years. However, the technique of Karamata allows you to look at ratios, as we will see. Okay. Let me take a pause and see if there are questions. Okay, so what we do is we let beta to be, again, I shouldn't use the mouse. And so you might be dizzy by now, but I'll try to be more careful. Okay, so we let beta to be equal to the sum of x sub i's, the x sub i's are IID, to the alpha. Then 1 over the sum of x sub i's to the alpha, once I fix omega, the left-hand side is a constant, and the right-hand side is a constant as well. So I have 1 is equal to 1 over alpha, lambda, integral lambda going from 0 to infinity, lambda to the alpha minus 1, e to the minus lambda summation of x sub I d lambda. Now, if again I have fixed omega, that means the x's are fixed. If I multiply by x1 square on both sides, I can then use Fubini's, use the expectation on both sides, and I have that the expectation of x1 square, oh God. Okay, no more touching. Okay, so expectation of x1 square over the sum of x sub I to the alpha is equal to the expected value of x1 square over 1 over gamma of alpha, integral from 0 to infinity of lambda to the alpha minus 1 e to the minus lambda summation of x sub I. Now, again, so this is our mixture, is a gamma mixture, and we take the expectation inside, and we have that the integral from 0, so the expected value of x1 square over the sum of x sub I to the alpha is equal to the integral from 0 to infinity of lambda to the alpha minus 1 over gamma of alpha, expected value of x1 square. Now, when we look at the right-hand side, we have the expected value of e to the lambda minus lambda sum I going from 1 up to n times x1. Now, if you notice, we have x1 times e to the lambda x1 plus the sum of x sub I. And x1 squared times e to the minus lambda x1 is independent from the sum from 2 to n of x sub I. So I can take the expectation of x squared e to the minus lambda x1, and using independence, write the top, okay, the second line, the third line, as the expected value of x1 squared e to the minus lambda x1, expected value of e to the minus lambda summation I going from 2 up to n d lambda. So then, using the fact that we have IIT variables, the second expectation above this expectation becomes the Laplace transform to the n minus 1. And we now have to deal with the expected value of x1 squared to the minus lambda x1. But this is just the second derivative with respect to lambda, okay, of the Laplace transform. Because if I have e to the minus lambda x1, I take the derivative with respect to lambda, I get x1 e to the minus lambda x1. If I take the second derivative, I get x1 squared e to the minus lambda x1. So the expected value of x1 squared e to the minus lambda x1 is basically the second derivative with respect to lambda of the Laplace transform. So that's how we go from this line to this line. Okay. So now another lemma used to obtain the proof is the expected value of x1 times x2 over the sum of x sub I to the alpha. And one can write this by using the same trick as the expected value of x1 times x2 over gamma of alpha times the integral lambda to the alpha minus 1 e to the minus lambda summation of x sub I d lambda, which is equal to the integral lambda to the alpha minus 1 over gamma of alpha, expected value of x1 e to the minus lambda x1 times x2 e to the minus lambda x2, using the same trick I used before of independence, times expected value of e to the minus lambda sum I going from 3 up to n xi. Now, this is by independence, and I can rewrite here. I have the three terms. Okay, so after the integral on lambda to the alpha minus 1 gamma of alpha, I have three terms, three random variables, which are independent. So, and the first one is basically the expected value of the first one is the Laplace transform of your variable. The expected value of the second one is the Laplace transform of x2. And the third one is basically the Laplace transform of your variable to the n minus 2, because I have n minus 2 variables left. So basically, that line by independence is equal to the integral from 0 to infinity of lambda to the alpha minus 1 over gamma of alpha, the derivative of the Laplace transform square times the derivative of times the Laplace transform to the n minus 1 d lambda. Okay. Now I put this together. So I put lemma 1 and lemma 2 together to finish the proof. So I use the fact that the sample variance is equal to, it can be written in this way. So this is sort of homework for students. You have that is equal to the sum of x sub I minus xj for 1 less than I less than j less than or equal to n over 2. And this is divided by n choose 2. That's the sample variance. And so when I want to calculate the expected value of Sn squared over xn bar to the alpha, that's the same as n to the alpha over n choose 2 times the sum of the expected value of xi minus xj squared over the sum of xi, I going from 1 up to n to the alpha by using linearity of expectations. Now, I want to remark that decoupling, linearity of expectation is a decoupling operator. Because on the top, we have a sum of dependent variables, but once you take, by linearity of expectation, you're looking at the sum of the expected value of the marginal distributions. So you can replace these by independent variables and then take the expectation outside. So I guess the first decoupling result is linearity of expectations. Now, okay. So is there any question about that? I think this is important because one can develop a theory, a decoupling theory, on the basis of extending linearity of expectations. I was going to talk about that, but that's a different talk. Anyways, and that gives you a lot of flexibility. So by linearity of expectations and the fact that I have IIT variables, the second line is equal to n to the alpha times expected of x1, x2 squared over the sum of x sub I to the alpha, the expected value of that. Now, I am going to expand this expectation, the x1 minus x2 into x1 squared minus 2x1 x2 plus x1 x2 squared, but xi's are IID. So this can be written as the expected value of x1 squared. I was dividing by 2, but I have 2 of them minus 2 expected value of x1, x2 over the sum of x sub I to the alpha, but I have 2 on the bottom, so that's how we obtain this line. And that's equal to, by using lemma 1 and lemma 2, is n to the alpha over gamma of alpha integral from 0 to infinity of lambda to the alpha minus 1, the Laplace transform to the n minus 1 times the Laplace transform of lambda, phi of lambda, minus phi prime of lambda square d lambda. So this ends the proof of the result. So now I go to applications of this result. So suppose that we have exponential random variables with parameter 1 over beta, with mean 1 over beta. Then one can show that the expected value of Sn squared over the sample mean to the 1 is equal to 1 over beta times n over n plus 1. Now, I want to remark that since we have a parameter that depends on the distribution on the right-hand side, for exponential random variables, the power of the sample mean is not 1, because the right-hand side is not roughly a constant. In this case, it's 1 over beta times n over n plus 1. Okay, so the way to calculate that expectation is by taking the Laplace transform of the exponential, which is beta over lambda plus beta, the first and the second derivatives, and plug them into the formula that I proved to get, in the end, 1 over beta times n over n plus 1. Now, the next result shows that if you have exponential again with mean equal to 1 over beta, in that case, the coefficient of variation is equal to 1, because the variance over the mean square, the variance and the mean are the same, and the mean square are the same for exponential random variables. So the coefficient of variation of the population is equal to 1. In this case, Taylor's law applies with a power of 2. So we have that the expected value of Sn squared over x bar n squared is equal to n over n plus 1. So I'm going to show how to do this calculation. Now, let's think about the inverse problem. So suppose that you have, if you plot x bar n squared against Sn squared, and that gives you roughly a straight line, or the relationship is n over n plus 1. So this is a way of testing whether or not your variable is exponential. If you have a line, a straight line, roughly straight line, then your variable is exponential. So it's a way of using your sample in a different way than we're used to get your sample to infer what the distribution of your variable is. Typically, in order to find the distribution, we use the Kolmogorov-Smirnov test, but this is a different approach to doing that. So again, what we have is, so if you use the formula that I presented, you can calculate the expected value, and that's equal to n over n plus 1. The coefficient of variation squared is equal to minus 1 n plus 1, because I have the sample coefficient of variation is n over n plus 1, the expected value, minus the actual coefficient of variation, which is 1. So I have minus 1 over n plus 1. So an important random variable, an important quantity when you are doing estimation is what is the bias of your estimator. In this case, our estimator for the coefficient of variation is the sample mean square over the sample variance square over the sample mean to the square. So prior to this, people didn't know so this is a new result, what the bias of the sample coefficient of variation was. Using this technique, you can calculate it. Now, if you look at, so the sample bias, the bias of the coefficient of the sample coefficient of variation square is -1/n+1. So if you have n equal to 3 or n equal to 2, then you have that this is going to be -1/3, which is basically giving you that the coefficient of variation, whereas it should be 1, it is the bias should be 1, the bias is -1/3, okay? And so this allows you to do calculations with respect to the mean square error. In particular, the variance of Sn squared over x bar n2 square is given by the equation here, which is basically asymptotically 4/n. So this gives you the mean square error of the coefficient of variation. And it tells you how variable the coefficient of variation is when you have an exponential random variable. The sample coefficient of variation is, which is important when you have a small sample size. So the lesson here is when you have a small sample size, either you don't use the coefficient of variation, or if you know what the distribution is, this gives you what the coefficient of variation is. The mean square error of the coefficient of variation is the sample coefficient of variation. Now, what I'm going to do now is to provide a concentration of measure result for Taylor's law. So again, I am looking at different locations, sample size J. Now, in this case, we have a double array of non-negative variables, okay, of possibly related subpopulations. So typically, in Taylor's law, in the use of Taylor's law, people assumes that the subpopulations are independent. But this result, this approach to Taylor's law allows you to consider situations when the subpopulations are not independent. Then the tail probability, the probability that your sample coefficient of variation minus its expected value, which is basically the variance of the coefficient of variation, the sum of the variances over m is equal to 1/epsilon, actually the square should be raised, over m squared times the sum of the variances. So we have a concentration of measure. We can calculate the right-hand side if you know the distributions, and that gives us a coefficient of variation for the sum of the squares. Now, applying the above result to exponentials, when we have the same sample sizes, we get that the sum of the sample coefficient of variation minus n/n+1. You remember the sample coefficient of variation, the expected value of that doesn't depend on the mean. So if you have a sequence of populations that are with arbitrary means, the sample coefficient of variation, or the deviation of the sample coefficient of variations minus n/n+1 squared, the average of those is less than or equal, again, than 1/epsilon, the square shouldn't be there, over m times n, 4 n over n minus 24 over n squared, little o of n squared. And again, I just go back to the remark before that our approach to, our approach to the coefficient of variation and Taylor's law gives us better variance. In this case, sorry about this. I don't know what's happening with my computer. I hope, at any rate, for nj equal to 20, the right-hand side should not be 1.449, but 0.449, that's a type. But you see the variance of the coefficient of variation when you have, no matter what the mean is, the variance of the coefficient of variation for nj equal to 2 is 0.08, but the variance of the log of the coefficient of variation is 3.97, a very big difference. The same thing for nj equal to 2, 0.3 against 0.9. For n equal to 10, it's 0.2 against 0.257. And for nj equal to 20, it's 0.15 and 0.449. Now, this can find applications in, for example, mathematics of finance, because one can, for heavy tail distributions, one can calculate, for some heavy tail distributions, one can calculate the coefficient of variation or the bias of the coefficient of variation. And oftentimes in these studies, you have a sample size which is small, and this will show you what the bias of your sample is. Okay, any questions? Now, I end this talk by showing this is a paper that we have submitted with Paul and Yahya, and which is on Taylor's law of fluctuation scaling for weakly dependent processes. So what we have is, so in a forthcoming paper with Paul and Yahya, we show that Taylor's law with exponent 2 holds for the case of weakly dependent variables with appropriately defined variance. In addition, we introduce a central limit theorem of the self-normalized empirical version of Taylor's power law, in which the sample variance is divided by a power of the over the sample mean. Our framework is of interest in the context of ergodic Markov chains, infinite moving averages, arch and Garch models, where the family of distributions is a parametric family. This self-normalized statistic is proved to be consistent, and the consistency result is reinforced by a central limit theorem. Now, in the context of Taylor's law, what we have is the first the first actual central limit theorem for Taylor's law. Prior to this, the central limit theorems were obtained in the context of what is known as 3D distributions, which basically works with the populations as opposed to using the samples. So this is the first true central limit theorem. Both results together provide us with an asymptotic test of goodness of fit to check whether the corresponding dynamic Taylor's law indeed holds. So remember that when we have a Taylor's law, you can calculate the bias, and in particular, the expected value. So if your line is a straight line for the alpha equal to 2, then you know that the distribution of your statistic is exponential. Okay, so, and this ends the talk. Wrapping up, so what I have done in this lecture is to develop the theory of self-normalization. The first part was developing the theory of self-normalization, extending the law of the literary logarithm to the case of arbitrary variables with arbitrary means and dependent structures. And I showed how these results have been used in the context of machine learning. And that's a very active approach to finding optimal algorithms in machine learning. I can send you some of the papers related to this by people at Google, Google Mind, people at Yahoo, and so forth. So it's a very active approach to machine learning. The second part of the talk involved the study of Taylor's law in the context of self-normalization, which is related to the coefficient of variation. And this is a scale invariant law in that the power of the power alpha in the Taylor's law is invariant under the different okay, so different scales that are, the measurements could be in different scales. For example, when you look at the population density, you could have thousands of people. Your sample could be in thousands of people or in hundreds of people, and your result is invariant with respect to the sample size. So I have shown how to use Taylor's law and the coefficient of variation to test for a distribution. And our work with Paul and Yahya extends this to the case of weakly dependent processes. And and that's the end of the talk. And thank you for being patient. Are there any questions?
No.
Yes. Is there a question?
May I just recall a detail, if you don't mind, that in this dependent case, in fact, you said that people use a different form of the variance, which is indeed not the individual variance. And in fact, there is no strict difference between an exponent which is 2 or not. That's exactly the same, in fact. But anyway, that's true that it's a good way to understand better the things, to think about an exponent too. So thank you, it was very nice.
Oh, thank you, Paul. Thanks to everybody for the patience. I'll be here for a few more minutes in case you want to see more results. At any rate, thank you very much. Thanks a lot.
Thank you.
Talk.
Okay.
It will be found on the internet on So You Talk. I don't know what happened. I should apologize because I don't know what I did with with to process the content, and so it will be on the website. Thank you.
Okay, so thank you very much again, and I hope that this motivates some research. There are still a lot of problems related to Taylor's law and its applications to biology and a number of fields, including physics, mathematics, number theory. So it's a very fertile area, which finally, it took several years before one, deep approach extends the results that were basically parametric to a non-parametric setting. Thank you very much again.
Yes. Thank you. So I wish you all the very good year, and I think this session will be the last before for 2020, for the year 2020, and let's meet again next year for more things.
Ok. Bon,